Thank you, Avi. Good afternoon, all. Today I have the pleasure of talking about some in-situ observations from a suction bucket that we monitored. I'd like to thank my co-authors, James Smith and Avi. Maybe we should have done a double act, but next time. This paper follows on from a paper we presented in the ISFOG conference in 2017. That paper looked at some measurements from Borkum 1, and this paper looks at some measurements from suction bucket jackets in Borkum 2. In both cases, the caissons were installed in dense sand, typical of the North Sea, and in both cases, we used the measurement data that was got from the suction bucket jackets to look at bucket stiffness and bucket drainage. And this paper confirms some of the findings that we presented in that earlier paper. And currently at the moment, Ørsted are installing 66 suction bucket jackets in the Changhua 2204 project. So maybe the next ISFOG conference, we could present some findings from that to triple confirm our findings, hopefully. So yeah, today I'm just going to look at bucket drainage, but in the paper we also talk about bucket stiffness. I'm going to use the measurements that we see in figure 1 here. And in figure 2, we see a time series of force applied to the bucket lid, calculated from the strain gauges on the bottom of the jacket, and corresponding water pressure resisting that force underneath the lid, calculated from the pore pressure sensors just beneath the lid. To examine the drainage, we set up this partial differential equation, which you can see details in the paper, which examines the rate of change from undrained to drained conditions. And in the green, you can see the kappa parameter, which is the proportion of the input loads resisted by the water force. And in blue, you can see tau, which is kind of the time coefficient as the water pressure goes from drained to undrained. And you can see this behavior in the time series. After 400 seconds, the load on the turbine changes because the wind direction changes and the turbine yaws. And this causes a buildup of excess pore water pressure beneath the bucket lid, and then this gradually dissipates over time or drains over time. But to look at this drainage for longer time periods, we move from the time domain to the frequency domain using a transfer function to examine the kappa and tau parameters. And here you can see in figure 3 a transfer function for a single day of data. And what this shows is that the gain, or the kappa parameter, is approximately 0.5, and that means approximately half of the pressure high frequency loading that is applied to the bucket is taken by this water pressure beneath the lids. And this was quite consistent across both of our measurement positions in 6 buckets that were measured, whereas the drainage, the tau was 60 seconds for this particular bucket, but actually varied a little bit from all the 3 buckets that we measured, from 30 seconds to a maximum of 2 minutes. And what does this mean for design, finally? I suppose the kappa can be used in bucket lid fatigue calculations as what percentage of that pressure is being taken by water pressure, so you don't have to consider that for fatigue. Whereas tau, the drainage time, can be used for sustained load calculations. And for instance, for design, we took a much more conservative value than what we measured in the field. So maybe for the next project, we can be a bit more progressive with that parameter. And with that, I'd like to thank you very much for listening.